Yeah, the real choice.
Or maybe these are just, we're not planning anything long.
Oh, you mean 10 minutes is long?
Thank you.
10 minutes maximum.
The idea of the past
Long for
couple
the
is that they're
subject.
supposed to be about 3 minutes long, but
It's
that has never come close.
Yeah.
It has been printed in a little awkward way, so it's not on long age binding, but short age binding. So you need to flip it as ancient papyrus from Egypt. And I will be soon killed by the chair or by the departmental administrator for paying too much for this printing things. So let's wait until we have everyone. Should be.
I see the CPM guys.
I shouldn't count this two. 1, 2, 3, 4, 5, 6, 7.
We're missing 3.
3 or 4?
Anas, Mead, and Queenie. And
Let's see what the order is on.
oh, Steve though. We're missing as well, so 4.
Maybe someone got scared and decided to drop the course right this evening.
No.
Didn't they send you the slides?
Yes.
Yeah.
Yes. And slides are there in the.
Wait, why are the first 6 names not in bold?
It's transfer of files from one computer to another one. Corrupts things and-
Oh, so it doesn't mean anything.
It doesn't mean
it's
anything.
really important.
It doesn't mean that before 6 are good and after bad or otherwise.
Yeah, it's
No.
average afterwards.
Let's make them bold as well.
I sent them a message.
Oh, thank you. Thank you.
I'm sure it's wrong.
Okay.
Wait for you guys.
So now we.
Two more.
So
We need and Queenie.
okay, probably we can start and hoping that they will appear. We have a couple of first speakers.
Yep.
Right? So who else is missing? Thank you for keeping to invest your time into this course. This is presentation session number 3. the idea is that the course consists of background theories for computational chemistry that helps to characterize properties of molecules and materials without making your hands dirty. And the lectures cover theoretical background, and practical sessions in the computer class cover practical aspects. And because it is very challenging to get these practical skills in a short time, we are practicing students teach students. So everyone gets expert in one or other aspect and passes on the knowledge transfer to the rest of the class. Because right after this session, we will try to apply these skills for mini research projects, and after today, everyone will be expected to know everything that was presented today. So it's not last time. It is your chance to ask the speaker if something is unclear. And here is where we are we are on number 22 in the plan of the course. So we will soon start new chapter, and there will be presentations of research projects at the end of the course. So there are 11 presentations. I've put here 10 minutes for each, but it is no. Try to be short. It's just upper limit, right? Taking into account that you'll spend a little time walking to the podium, loading the presentation, answering questions, walking back. So in case, I know that what I'm telling you is not funny anymore, but I just memorized this verbal formula. If you never seen Windows PC or PowerPoint, here it is. So your slides are organized by number and by the name of presenter. They are here on the desktop, and you look where you are on the program. And by the way, there is specific organization of the materials. So about first segment of several talks will show background of the way how to execute and analyze code. Then there will be focus on electronic properties, concept of density of states, with and without spin, with or without charge, with making an analog to Gaussian spin and multiplicity. Then there will be segment of presentations on optical properties, and last but not least, there will be a couple of presentations on reaction dynamics, molecular dynamics, and visualization. So those components are needed for successful modeling. So first presenter is Nathan Walker. So again, if you've never seen Microsoft PowerPoint, click here to start the presentation. And if you take more than 10 minutes, someone will start to kick you from the podium. Floor is yours.
So the main point of my presentation is to run you through how to prepare VASP input files to get your jobs to run. But I figured since you're trying to get VASP to do DFT for you, you should know a little bit about what DFT does. So the first couple slides are going to look pretty familiar. The whole idea is to just take some input, in this case position of ions, the number of electrons, and some energy tolerance, and generate output. And in this case, what you want is the total energy of the system. So once you have the position of the ions and the number of electrons, you can get an initial charge density, which will then let you calculate the potential. And you can plug that potential in the CHEM equation, which will let you get an updated version of the charge density. And from that, you can calculate a new updated version of the total energy, and that's where the energy tolerance comes in. If it exceeds the energy tolerance, you do it again. If it's within the energy tolerance, you get your output. And from there, this is a slide from quite a bit earlier in the semester. Again, you have input of coordinates, a time step, and an energy tolerance. And this time what you're trying to do is calculate the final optimized position and energy of this molecule you want. And so the important part is this, the UT sub n plus 1, that's the updated energy. So the previous slide I showed you is basically a longer version of this. Every time you get to this loop, part of this loop, it'll run through this until you reach the tolerance. And if you do that enough, you'll get updated geometry. So to make all that happen with VASP, you're going to need 4 files. You want the POSCAR, which stands for position. It's the coordinates of all your atoms. The POTCAR, which specifies the pseudopotentials that you're going to use in the calculation. There's the INCAR, which has a bunch of input parameters, and K-points, which specifies aspects of K-space that are going to be used in the calculation. The first one I'm going to talk about is INCAR. It has a lot of different parameters, and it lets you customize your calculation in a variety of different ways. Up here, it says ISIF. That lets you control whether or not you're going to calculate forces, whether or not you're going to let the positions of your ions get updated, and whether or not you can let the box relax in whatever way. Box, by that I mean how much vacuum you have around the molecule. Precision, that it's fairly obvious. It tells you something about how precise your calculations are going to be. Specifically, since VASP uses plane waves, precision will kind of specify the cutoff energy that the plane waves have. So low is going to be some low cutoff energy. The higher precision you go, the more energy values are going to be included, and the more precise your calculation will be. That's also reflected in cut. You can explicitly set a value in electron volts that you want to cut off afterwards. IBR ion, that's going to let you kind of control how positions are updated. So each time it goes through the calculation and moves the ions, you can control whether or not that update is going to be the best way I can describe it is there is one option that lets you kind of create an effective drag on the ions, so it'll kind of slow down how much they get updated. And there's a lot of other options besides that. There is a VASP wiki that has descriptions of all of these and more. And then POTEM, if you go back to this slide, that's what this delta T is. It controls the time step for the ionic position ionic updates. iAlgo, that controls the algorithm you use. That can factor into how fast or slow your calculation will go. And each one is just kind of coded in with an integer, 38 or 48. 48 I think will go faster than 38 typically. iSmear changes how your partial orbitals get smeared out. 0 is Gaussian smearing, 1 is Fermi smearing, I believe, but then there's a few more options beyond that. Sigma changes the width of whatever smearing you use. And its units are in electron volts, so right now the width is 0.01 electron volts. LReal will tell you whether or not you're going to do the evaluate projection operators in real space or reciprocal space. It's set to true, so it's going to evaluate those operators in real space. iStart, if you have iStart set to 0, it's not going to read in a wave car. It'll calculate your orbitals or initialize the orbitals straight away. If you set it to 1, it'll read in a wave car as input. L wave, if it's true, it'll output a wave car. If it's false, it won't. L charge will either output a charge car or not. This bottom one, LV tot, it'll do a similar thing with these two. It will either read out an output file containing potentials or it won't. EDIF G, that's the energy tolerance. If it's a positive number, it'll actually calculate the change in energy for each run. If it's less, if it's less than that number right now, 0.0001, it'll quit the calculations. If it's greater, it'll keep going. And if you set that number to less than 0, so if I just put a negative sign there, it'll actually calculate forces instead. So it's a similar concept, it's just calculating it with forces instead of energy. Okay. Then the next file is a POSCAR. Like I said before, it contains all the information about the coordinates of the molecule. Oftentimes we'll be starting out with a POSCAR.xyz file, and you're going to have to convert it to a POSCAR, so I thought I'd, in this first picture, kind of show you how to go about doing that. It's a little hard to read, but this command up here, /bin/rotate xyz. So there's a script, rotate_xyz in the bin folder. What that'll do is it'll take a POSCAR.xyz file, and it'll rotate according to input that you provide. Normally you're not going to want to rotate it, so you just enter in all zeros. The reason you want to do that is because it'll output a file, POSCAR_ROT_TINC_XYZ. You're going to want that file for the next command. It's Perl. Perl is just a programming language. So this tells you to run a script written in Perl. In the bin folder, and the script is called TINC_VASP _watt.pl. And then it takes that POSCAR ROT file from earlier as input, and you want to type POSCAR to get just a regular POSCAR VASP file as output. And then these three numbers change how much vacuum you add outside of the molecule. There's three numbers, one for X, one for Y, one for Z. So here I added 8 angstroms of vacuum on in all three directions. And then the result you get is this. Just a list of all the coordinates here. Up here it tells you the types of atoms you're using. Here it's bromine, cesium, lead, and this right here is the like the coordinate axes you use. Right here it's 9.8, 9.8, 9.8, X, Y, and Z. You could have off-diagonal elements, but in most cases your ion or your molecule is going to be oriented, so there's not going to be any. And then over here you see all these T's. What that means is when it's running VASP, it'll update the positions of all these atoms with T next to it. If you change it to F, it'll fix those. So if you ever need to target what atoms you want to move, that might be a good way to save a little time if you know everything else is good. Okay, and then the next two, K points and POTCAR. K points, K space is reciprocal space to position space. So this is a little example of what a K points file is going to look like. The first line is a comment, but it's useful to kind of say what it is. In this case, it's an automatic mesh. So that means it generates all the points in K space automatically, and specifically that is told, a VASP is told that with this 0. And then Monhorst pack, that's just a particular method of generating an automatic mesh. And then down here, the 1, 1, 1, that tells you how many subdivisions there are in each lattice vector. So since all three are the same, there's the same amount of subdivisions in each direction. If this were a 3, there'd be more subdivisions in this direction than the other two. And then this bottom one, this bottom line with the zeros, that's the shift in K-space. Right here it's set to 0. I've never done it with anything else. Time, okay. And then with POTCAR, I didn't show one because it's a fairly big file and I don't think it's really useful to look at it. But what it does is it specifies the pseudo-potentials of that you're going to be using for your system. That'll change depending on what you're using, and you want to match up the atoms in your system with the POTCARs you use. So in this case, bromine, cesium, and lead. That means you want your POTCAR to include information for bromine, cesium, and lead. And then once you have all that together, you can submit it.
Okay, thank you. Although he used all his time, but you're welcome to maybe one quick question. Everything was crystal clear? Question one?
So the
Question-
T is, so F stands for fixed and T stands for?
Translate.
Okay, then let's thank Nathan once again. And the next presenter is Sudipta Saha. So Nathan told about the input files, and Sudipta will tell about the output files that come out of the successful calculations.
Hi everyone. So, so for our today's presentation, I will basically focus on the VASP output files, and then I will discuss a little bit about how to calculate the density of state, and then the charge curve file. So, usually after simulation, for input file we need 4 different input files that has just been described, and after the simulation of any calculation, usually it produces several number of output files, and I am going to discuss the major input files that we basically need for this course, or maybe for next projects that we need for density of state calculation, charge density calculation, this type of stuff. So first of all, the outcurve file. The outcurve file is considered one of the most important output file for VASP simulation, and it gives information about the electronic and geometric conversions. So in this outcurve file, usually you can it contains the free energy of system, the external pressure of the system, and it takes the time taken, the memory taken for the calculation, and all the informations related to particular VASP simulation. And that CHG curve file, there is another file called a CHG file. The CHG file and CHG curve file both are almost same, and like the main purpose of these two files are same, and the basic purpose is basically calculating the final charge density. And if you want to run one calculation for 2 or 3 different segments, and then this CHG curve file helps you to start calculating the charge density from the final condition of previous segment. And the concurve file is basically another version of postcard file. So okay, so for postcard file, postcard file is used for the input, and in postcard file you will give the atomic positions of the positions of the atoms you are using for your structure, and that is the initial structure, the initial position. And after every iteration, the position will change, and the new position will be saved in the concurve file. So suppose you are using 500 different 500 iterations. So the concurve file of one specific calculation will keep all the atomic positions, geometric positions of the final step of the iteration. And if you need the final step of this iteration for another calculation, or maybe for another segment of the same calculation, in that case you will use this concurve file renaming the concurve as postcard for the second segment or for another calculation. So this concurve file is the only output geometrical file. So, and after that, the CHG file, that's what I have just said, that CHG file is the same as the CHG file. The main purpose is to calculate the total charge density. And it's also used for visualizing the charge density. And we will see the charge density visualization at the very end of today's presentation. And the EIGEN val file, this file basically represents the eigenvalues that are considered for the CHEM calculations and for each k points, and it is used for band structure calculation. And the Dosker file is used that I am also going to use for the calculation of density of state. And the OFCAR file, it's a binary file, and it contains the following informations, like the number of bands, the initial cutoff energy, the initial basis vector defending the supershell, and also the initial eigenvalues and initial Fermi weights. That's a binary file. And after that, we have the Orzika file. This Orzika file basically contains the convergence issues, like the how many steps we need for the convergence. And suppose I am for one specific calculation, I am setting the NSW value 500 or NSW value 100. So in the Orzika file, when you open the Orzika file, you will see the following informations, and what those basically mean. Like after every iteration, it will show you the number of electronic steps that has been completed so far, and also the current free energy and the change of current free energy from the previous step, and also the charge in band structure energy, number of evaluations of Hamiltonian acting onto the wave function, and also the RMC, that means difference between the input and output charge density. So these are common output files that we will need for our VASP output analysis. So now I'm going to talk a little bit about the density of state, and the first one is very typical and common definition of density of state. That means the amount of states that we have at a specific energy level at like per interval of energy at each energy level. That means when the density of state is high, that means we have so many states per interval of energy that are available for the occupation. And when the density of state is 0, that means we don't have any free state for occupation of energy. And for calculating the density of state, I have used this material. This material is called LLGO, and first L represents lithium, second L represents lanthanum, third G represents zirconium, and O represents oxygen. And this is a screenshot of the Poskar file. So as we can see that in this structure we have 28 lithium, 12 lanthanum, 8 zirconium, and 48 oxygen. And this is a basic unit cell information. So in A, B, and C, we can see that the length is the same. That means this is a cubic structure having volume 1108. So I have calculated the density of state for this one. So how to do that? So for doing this thing, we will have to relax the system first. Like and we have already done this type of things in our previous classes, that we will have to relax the structure. And after relaxation, 4 different things can happen. The first one is the ground state condition, the second one is at anion, third one is cation, and fourth one is excited one. So what we basically need, do we need to calculate the density of state for the ground state condition, or the anion or cation or excited condition? If we need for anion, cation, or excited condition, then we will have to do the geometrical optimization again with a different Tinker file, and in everything else will be the same. Like the K points file and Potkar file will be the same. I will just copy it from the previous file, and the Poskar file will be the Concur file of the previous relaxation step. And the in Inker file you will have to include 3 different new parameters. Like you are okay. Okay. So you will make NSW value 0. That means only one state, and you will use the number of electrons like if it's
We need to finish everything. 1 minute.
Okay.
For everything.
Yeah, with this command grep any LE outcome, you can get all these informations, and after that you need to get a few more informations for the calculation of density of state. So with this command you can get and you can get this chart from outcome, and as you can see that at 300 step it's 2, at 301 it's 0. So we can use this value for the later calculation. Here for obtaining the number of electrons, use that command, and then for obtaining the Fermi and alpha beta energy, use this command I have written here, grep Fermi outcome, and you can get these informations from outcome. And after that, run the script. I have written the script so that you can use it for copy it from here from a presentation, and use the information that you have extracted from earlier with the commands. You use those informations here. The information has been made in red mark, and after using these commands, I have calculated the density of state using GNU plot software. And then the CHG curve file has been used using the Vesta for visualization, and this is the output of the CHG curve visualization. So that's it within very short time.
Okay. Any questions? Okay. Japan was first, Levi is second.
So in your cationic and anionic charge density calculations, you consider the n as W equal to 0. So
Yeah.
why you just did a single point? Don't you think there is some geometrical reorganizations or?
In ground state condition, you are using any LC value default. Default values means the not anionic, not cationic. So if you make the NLE value equal, like how many electrons you are moving or adding, then you can use. You are not using the ground state condition. I am just prepared the presentation so that if you need ground state, so do normal relaxation. If you need anion or cation, do one more extra step. But if you are determined from the very beginning that I am only doing the cation, so you can do it at the very beginning, like only one step. You just use the NELE parameter in the Incar file. That's it.
Other quick questions?
So you said that your system is cubic, but your off-diagonal elements in your possible are not 0. Is it cubic?
Sorry.
Is your system cubic?
Yeah.
No.
A, B, and C.
No, except that your system is not cubic.
Okay.
Any more questions?
Thanks. I'm not sure.
So next presentation is by Ben, and his talk is very important to help us how to get the job start as soon as possible and complete as much as possible.
Yes. So we talked about the input files and the output files. Now we need to talk about how to go from one to the other. So a brief overview, we're going to touch briefly upon the stuff needed for Thunder, the PBS scripts and the Q types on Thunder. And we're going to talk about script types on NERSC and the Q types on NERSC. Then we're going to go into how to run the jobs, which is the easiest part of all this, and then some tips that I have. So looking on the NDSU clusters, at NDSU we use this PBS, or the portable batch system. We use these files to submit the jobs, and it has many different arguments. So you have stuff like the queue name, what queue you want to submit it to, the nickname for your job. I nickname all mine Steve. So I'm glad some of you found that funny. So we got some nodes, like how many nodes you want to run it across, and how many processors per node, how long you want it to run, you know, the amount of memory you want to use, you know. There's another one that you have to use, I believe, about like what group you're a part of. That's not listed on here. But the important part is the path to the executable, which is important because you're running VASP, and the system needs to know that you want to run VASP. Unfortunately, I don't actually know the path to the executable. So that's some important information I don't have. So look up the queues on the Thunder. So we have Condo 1 and 2, unless you're part of the Susan or Kinana groups, you don't have to worry about them because these are privately owned, well, not privately owned, but privately rented queues. You have the default, the long, medium, and short. This is what you're mostly going to be using on Thunder. The major difference is the queue time, like the wall time, rather, how long you can run the jobs, and also, I guess, queue time, how long you have to wait, because if you run something in def long, you're going to be waiting a lot longer because that has lower priority. So we have def devil, which I couldn't really find exactly what that's for. Okay. And then we have preemptable, which is this queue for, like, basically your job can be preempted. However, in exchange, you can use up to 100% of the cluster, depending on how free the cluster is. And then we have Big Mem, which has a terabyte of memory per node. So that's useful if you're running a job that needs a lot of memory. So moving on to NERSC. In NERSC, they use SH, which this is one of the files that Dimitri has on NERSC. So we have sbatch debug. This is the partition name or the queue name. We have number of nodes that we want to use, the wall time, license, the job name, and the constraint, which is used for specifying which server you want to use. And then you load up VASP, and that is what SH looks like. Queues, this is specifically for Cori, but you know, it's all the same. Regular is your standard queue. Interactive is for running interactive nodes. I don't foresee a need for that really, because you know, we're going to be running mostly batch jobs. Debug is for running debugging jobs and the such. Premium, well, costs a premium, but allows you to get jobs done much faster. Scavenger just kind of finds bits and pieces of other nodes and kind of. And then Big Mem, it's the same as well. So it's the same as on Thunder. So.
Wait. Sorry to interrupt.
Yes.
Before you finish, can you go back one slide and tell what you need to change in this script if you want to submit it to regular instead of debug?
Okay, so you would need to change this partition name from debug to regular. So you just need to change it to the queue name.
Okay,
so.
good. And the sbatch minus n1, should it always be 1, or you can change this number?
Well, I'll get to that in tips.
Okay.
But yes, so running jobs, you can run jobs. You can run on Photon, which I don't really recommend, but for the sake of completeness, you simply run VASP in the folder that you have all your files. In Thunder, you simply do qsub PBS in the folder that you have your files, and in NERSC you do sbatch, name of your SH file, in the folder that you want to run it in. tips for faster turnaround. Spread long jobs over multiple nodes. So as he was alluding to earlier, you can run a job on multiple nodes, not just one. This is particularly useful if you have a job that you expect to take many, many hours, days even, but yeah. So use the queues to your advantage. So if you know that your job isn't going to take that long, there's no need for you to put it in the long queue. Put it in the short queue, and sometimes even it'll just be to your advantage to submit a job multiple times to the short queue rather than wait for the long queue to open up at times. Don't run significant jobs on Photon. Photon's not designed to do that, so it's not going to be very fast. Go to Thunder or NERSC to run any significant jobs. Fewer people are awake at night. This is a true fact. And so there will be less jobs running at night. And so either you can stay up all night or you can run jobs and then just wait for them to run overnight. And then finally, if all else fails, be patient. Go and do something else. Go read a book or go work on other homework. Submit some more jobs.
Okay, let's thank Ben for these instructions. Any questions? I do have one. Can you go back to more?
Which one?
One more? Here, yes.
Okay.
So if you want to use more than one node, is it sufficient to change only the number in here? Would it be sufficiently efficient, or should one change anything else in the script?
Based off the way that you asked that, I'm guessing. I'm guessing that I would need to change something else as well.
So what the number after minus n in the srun stays for?
I think that's number of CPUs.
Okay.
So
if you use 2 nodes instead of 1.
you would need to double the number of CPUs.
Exactly.
So.
More questions to Ben? If no, then thank you once again.
Oh.
No, it's a
Quickly.
short question. So
Okay.
why
Questions, please come in and.
But if we don't change that one, but we change the n equal to 2?
Then it'll still run on 2 nodes, but it'll only run on 12 CPUs per node.
Just pushing my way and set up your presentation.
Okay.
If there are no more questions, let's thank Ben for the 3rd time. And the next presentation is by Gage, so he will entertain us by nice images.
Yes, I do love my pretty pictures. So this is a bit out of order in terms of entirely what I'm covering, because I'm also going over some VMD stuff, which we don't really get introduced to until Kurt's presentation last. But for starters, what I did was I just used the TI408 molecule that we had previously done in the lab. Again, just calculated the partial charge density with VASP. And I kind of rushed through this a bit because we've already done this. Just wanted to point out in the in-car file the changes we had to make, these 39 bands and the -8 and 0 here. This is inside the directory. This was taken after I ran everything, so I'm not entirely sure what should and shouldn't be there right now in the presentation. The important parts that we want to look at for the VMD that I put in were the charge car, conf car, and then I can't remember if the cube files or just the regular version, but these files here are what we're kind of looking at in the presentation of the partial charge. Here we just have the coordinate system and whatnot. Just further down that partial charge file, I didn't give myself a whole lot of context for this, so I don't actually remember what that was. It's just a lot of meaningless numbers at this point. But in order to get the partial charge set up for use in Gausview, we do need to convert the original file that I showed into a cube file, which I'm not going to go over how to open Gausview again. I've done that enough. We just open whichever file we're kind of looking at, and then in the results we go to select surfaces and contours. Once in there, we want to go down to the surfaces here, and I already have it open, but just drop that down, new surface, and it'll pop this up. You have to change the density a bit in order for it to really, in order for you to visualize it well, because there's probably just a giant blob. And here we have a monument to my failure, because I just transposed something, but yes, it's supposed to be oxygen here. This is the HOMO orbital levels, so clumped around the oxygen. However, if we go to the lowest unoccupied, the orbitals are now clumped around the titanium. And now just a quick overview of VMD, which I'm not going to go ahead and download because we're doing that later. In order to open things up, we just have to browse for whichever file we're looking for. So what I ended up, so what I did here was I basically opened 4 different molecules. They're all overlaid on each other, but again, I have the cont car, charge car, and then the 2 cube files. This is kind of in the settings that I was messing around with to make everything look pretty. Ignore the ISO values here, because these were all taken at the exact same time when I had 2 of them kind of just invisible. But for the charges, you want to just set it to an ISO surface, which will allow that to kind of show up. And you can set it as like little points, but those are kind of hard to see on the presentation, so I just have a solid surface here. Change the color, which that is the color, it's just not showing that. So here we just have the charge car file. We only have the charge showing up on the oxygen itself. When we look at the partial charges, they follow the same behavior that they did in Gausview, where on the HOMO they are held around the oxygen again. I do kind of disagree with this title of this slide here, because it looks like they're huddled around the titanium. But again, I forgot which one was which, so I can't really throw stones. I don't remember these slides. Okay, yeah, okay. Yeah, I like this title a lot better, because this is also showing a different, yeah, this is showing the wireframe here, which is, we have a different method of visualizing how exactly these are. They're more like clouds really than real physical objects.
Okay, let's thank. Questions? What is your conclusions? Each talk should have conclusion either as slides or as verbal. How will you conclude?
I don't know, it's kind of a...
It doesn't need to be sophisticated. You can say orbitals are nice looking.
Well, they are.
Good. More questions? Jebet?
So which one you would prefer, Gausview or VMD?
Well, VMD is going to allow you to do a lot more stuff, but it doesn't like me, so... Gausview for the time being, but I acknowledge that it's probably not the better one.
More questions? I have a couple. So on this slides, nicely prepared by Nathan, where are your part charge files? And also, if you find typos to correct, you are welcome to. Like, which symbol in this slide corresponds to pore charge files?
You put me on the spot here with this. Well, it's not that.
You're right, it's not that. But you started with right equation. It is exactly equation, quantum equation for pore charge orbitals.
Also, it is somewhere in here.
Yeah, okay, let's go symbol by symbol and decide whether it is right or not.
I think it's either that one or that one.
Wait, let's focus on one by one.
You can just ignore the hand.
No, not this one. Next.
I'm not sure which one you want me to point at right now.
Letter E typically used for energy. And it shouldn't depend on position. Okay, what else?
Well,
Theta.
yeah.
So your claim is that letter theta is for quantum orbitals, right?
Not yet.
Yes, say yes.
Oh, it is.
Yes, thank you for correct answer. And if you want to wait, stay here. If you want to correct Nathan, put I symbol here. More questions to this nice talk? Once in your presentation, you did told that you are where you compare three things. You are opening cube files with VMD. Is there a need to use VMD for cube files?
Well, I open them up in Gausview.
You can
if
open
that's
them
your
in
question.
Gausview and then you do not need VMD. The whole reason of using VMD is to open pore charge files directly without converting them to cubes. To save one step less. So you were able to open charge car and the same way you can open pore charge.
That makes sense, but I had already made the cube files, so.
They contain the same information.
Yeah.
And later on, everyone is welcome to open pore charge files directly.
Yeah. It's not really necessary, but it didn't change things in
Okay.
the grand scheme of things.
No more questions? Let's thank Gage once again. And Kevin is going to open our eyes. Let's go next.
One question. Did you teach momentum dispersion to the class or not? Like talking about?
You're the first one.
So I'm talking about a brand new topic.
Yes,
Okay.
and you can no more than 10 minutes.
Okay.
Try to fit in 5. So Kevin is opening our eyes in a sense that the whole VASP software is designed for periodic solids where overall electronic orbitals and electronic state may not sit still with zero velocity or zero momentum, but can have the non-zero translational motion. And the 5 key points and the subject that Kevin is going to present is a way how to address this overall net motion of the electronic structure in translational way.
Okay, so if I added notes here, if I go to PowerPoint, will I still see these notes?
Probably not.
Okay, I'm just gonna, can I just present like this then?
As you wish.
Okay. So as the professor said, I'm doing a momentum dispersion. So this is a new topic that we haven't covered in class, so I'm gonna go over it in like 5 minutes. So first, a really basic introduction to like what dispersion of electrons is. The dispersion, it's basically the ability of an electron hole to move through a material. Okay, so we know that crystal structures means that momentum may have many possible energies due to their periodic structure. Also, some energies don't have any momenta associated with them. And a band structure, it's a collection of all possible energies and momenta. And the properties of a band structure define whether the material is an insulator, semiconductor, or just a plain old conductor. So try to find how energy depends on a momentum. That's like really important. All right. Oh. Okay. So then another thing before I get into the actual coding of this is to define electric effective mass. So we all know that energy is equal to the momentum, which in this case is represented by K, so K squared over 2m. As electrons and holes move through materials, the atoms that these like electrons and holes are moving through, the atoms in direction they're moving in affects both of them, okay? So that's really important to keep in mind. Thus, the laws of mass and momentum are no longer applicable due to like non-constant mass. So this is an important thing to keep in mind. Okay, and since we didn't cover any of this in class, the rest of my talk is just going to be pretty much the code that you can use in WASP to make the graph. So for the rest of the talk, I'm just going to like really quickly go through this code and just point out some important things. So my intention for this is that once I go through this, you can just download this PowerPoint and just use the code in this as a template to make your own dispersion graph. So I figured that'd be the best use of my talk. Okay, so so the important things on this slide is that we made a new directory with that's titled TI408 per dispersion, and then we copied all of the files we needed from our periodic to our current directory, which is like represented by this dot here. And then we modified K points by replacing the periodic directions with larger numbers. So as you can see in this point, this first column, that's our Kx, that's our Ky, that's our Kz. So in our molecule right here, since it's repeating in the z direction, we made our Kz direction just 8, which is more than 1. And then since it's not repeating in the x or y direction, we just made our Kx and Ky directions 1. Okay, and then this is really important. We just copied our const car file from our previous directory. So we copied this, and then we changed it into our postcar file. There we go. Okay, so yeah, we copied our concat file. We changed it into postcar, and then we changed our in-car file. In in-car, we changed our NSW value, which made that equal to 0. So what is NSW? NSW is the number of optimization steps for nuclear position increments. So basically, setting a value of NSW equal to 0, that disables optimization of geometry, and it saves a lot of time. So if you're looking for something really quick, just change this like NSW value to 0. All right, and then after that, I typed in this command, this bin VASP photon, and then I just said more this file name ibzkbt. So then it generated this output. This first column, as before, is Kx, Ky, Kz. So as I said in these notes, since it's periodic, it is u direction only. Only the z values are like different from 0. So as you can see here, these values go from 0 to 0.5. All right. Okay, so then I used the grep command for to get particular things in the outcar file, and I just put them into a new file .allk, and then I just copied my all-K file into a new file called outcar1, okay? And then I just did more ALLK to get the information I need. So this first column is band number, band energies, and energy occupation. Okay, so then so in this example, we have our HOMO orbital, which is I is equal to 32, and the energy of our LUMO orbital, I is equal to 33. So the reason we did more ALLK was to find out which is our HOMO orbital and which is our LUMO orbital. So that's like really an important thing to know out of this.
Can I ask a question?
Yeah.
As we go, do you see, when you do this more command, if you see the whole list, do you see this list of orbitals once or more than once?
More than once.
And it is really important you make highlight it to the audience.
Okay.
How many times, if you have 4 values of K point?
4 times. Yeah, I didn't like paste everything in here. I just pasted one of this just to like save space. Okay, so what we're doing in these commands here is that we're basically extracting values.
I want to make a comment to everyone because we are having it for the first time. So in the setup that Kevin is presenting, the list of orbitals comes 4 times instead of 1, or it may come more if you request more K points. And energies of orbitals in each of these lists are not equal. So it is a set of lists of orbitals, each of which are slightly different. And the procedure that Kevin is reporting right now are technical details, how to extract energy of the same orbital, for example, HOMO, in each of these lists, and see how this energy depends on the overall momentum, overall velocity. Okay, let's keep going.
Okay, let's see. Okay, so what we're basically doing in these commands, for example, in lines 1 to 2, what we're basically doing is we're extracting values of k sub z, and we're placing it as a single column file in a file called kk. So that's basically lines 1 to 2. And then lines 3 to 5, what they basically are is that they're a command for creating a data column with all of our HOMO energy values. So all the commands for this are in lines 3 to 5. And then for like 6, the last 3 lines, we're doing the same thing, except it's our LUMO energy, okay? So these are all the commands for extracting all 3 of these values, creating them in columns. All right. Okay, so then we're basically taking our 3 column files we created in our previous step, and then these first 2 commands are basically just like taking those 3 column files and then just combining them into one single file. That's basically what we're doing in these like first 2 commands. And then these last 2 commands should look really familiar to you. We've done it like thousands of times. We're making a GNU prot out of the file we just created. And then in the last line here, we're converting that graph file to a PDF. All right. So that's basically what we're doing here. And the professor said that we should have our conclusion. This is basically the conclusion. If you've done all the steps right, this is basically, this graph is basically what you get. It basically shows how our band energy, which is in electron volts, depends on momentum. All right. So that's basically what we're seeing here. Let's see. Okay, so the top part of our graph, that's our LUMO orbital. So that's our lowest unoccupied molecular orbital. This is the graph for that, and then our lowest graph is our HOMO orbital. So that's our highest occupied molecular orbital. All right. So then this is our conclusion, and that concludes my talk. Thank you.
Okay, thank you. Any questions? I have a provocative question. Why green line goes up and red line goes down? Just as your vision, or if it is hard, at least why green line goes up.
Okay, so I remember you said this in an email last night. If I remember correctly, for an electron hole, the energy decreases as momentum increases. So that's why this bottom graph is going down.
And for electron?
And for an electron, which is this top graph here, as your momentum increases, its band energy also increases.
Okay.
So what would be the shape of this graph if you had to fit it to an analytical function?
Name of the mathematical function that would fit.
I don't know, but my guess would be a hyperbola.
Exactly, perfect. Okay, let's thank Kevin for nice answering the questions. Next presenter is Anas, and next 6 speakers should fit into 50 minutes. So please scale your presentation appropriately and appreciate effort of other speakers. So when we do final presentations, we should all plan and practice talks before so that they will be a little shorter. Right now we are returning from this sophisticated solid state thing to more important things for chemists and material scientists, when materials can be oxidized or reduced or can be excited by light.
Yeah, thank you. So the past speakers has given a bright picture about the input and output files of glass and the density of states. So my talk will be confined on the anion and cations and excited state analysis using the VASP and its density of state. So the first rule, make a new directory if you are doing the VASP calculation for the cation, anion, and excited, so that will you not mess up the data. And the copy the same like every VASP calculation we need for informations. That's postcard, K-point, and podcar and INCA, and it can be taken from the input file of earlier calculation. The only difference here is that in INCA file we have to do a little modification that can be done by using the command vi INCA. The number of electron has to be changed. For if it's a ground state, the number of electron is n, and if it is anion, it's n+2, and if it's a cation, it's n-2, and that can be changed by using the command vi INCA, and we can do the VASP calculation. So if you one more specific change in the INCA file here is that for the excited state we have to use a command of fervi and ismer -2. So that's will control the manual determination of occupation level. If ismer is equal to 0, that will be automatic determination of the occupation level. Same like earlier slides as shown, like the NSW here is 0, it's a single step process, and electronic configuration and elect can be determined depending upon the anion, cation, or excited state. So apart from this VASP output file, we also need certain other information for running the dose calculation. So here specifically I have taken the titanium oxide nanowire. So the other specific information to run the dose calculation is the number of state and number of electron and number of atom, the Fermi energy and alpha and beta energy. So the number of state can be determined by using the following command. That's grep nba outca will give you number of bands, and by overlapping command which is used to analyze the input file of the VASP output, and the number of state can be determined by the command wc state. And we also need certain other information like the number of electrons and alpha, the Fermi energy and alpha and beta energy, and the following we have to answer the following questionnaire like minimum energy, the magnitude, and the simulation cell dimensions. And after giving all this information, if you run the VASP, run it, the successful job will show you I am still okay. So you are good to go here. So this will help us to plot another graph, GNU plot, by using this command bin gn program dos for me, and we can convert the corresponding PS to the PDF by this command PS to PDF dos PS. And this has been well aware of another command that we can migrate our generated PDF to our local computer by using this command. And this is the plot of anion, cation, and excited state. You could see here in cation there is an unoccupied state in the valence here, but in cation it's fully in anion it's fully occupied, and cation it's unfilled. And in the excited state there is again some empty space in the valence, and it's been occupied in the conduction band. So since it's a semiconductor, there is a gap between the valence and conduction band. I assume if it's a metal, it might be overlapping. And if it's an insulator, there will be no band. Thereby I'm concluding my talk.
Okay, well, thank you, Hans. Any questions? It was crystal clear. No one has questions. Let's thank you for being very brief and helping us to finish in time. So, next presenter, please come up and start your presentation. So, Vini, will make our life a little set up your presentation. Set it up. So he will help those of us who in future may plan in the near future to model magnetic materials or reactive radicals where number of electrons is not even. So.
All right, so Anas has pretty much talked about most of everything I was going to talk about, but I'll just include mine. It just has like the spin-polarized DOS. So first of all, like Anas said, get your concar files and get your postcard files. And in this situation, we're trying to dope it, and so to do that, you just go into your use the VI command and open your postcard file, and include your the element you're trying to add in there, right here. Oops. And then also include the number of atoms you're about to add to. Does this have a
on the top? Maybe the battery is there. Okay, let's check.
Oh, okay. All right. Yeah, so include your element there, and then include your the number of atoms there. And right here, show use the VI command to like edit your postcard file to include your doped stuff. And also Photon likes VASP prefers orders, so you wanna also go into, before you run your VASP file, you wanna go into use this command to go and like put your VASP in orders in order that it's being presented in your postcard file. So like here you have oxygen first, and then you continue to provide it here with this command that I've provided here, and then you just keep doing that until, and then you copy the necessary files before you like in color, before you go ahead to like run your VASP. And yeah, when you and then run VASP. Okay, when you run your VASP, this for me, this is when I was trying it yesterday. This was my Untitled results that else provided. And then also if you want to get some information from it, like the total number of electrons, you use the command grep nel outcar. And then for my situation, it showed me the total number of electrons I had was 66, which is
Because you didn't replace titanium to vanadium.
I actually did. I
Interesting.
did.
Keep
Yeah,
going.
but yeah, okay. So, well, it gave me 66, but if it didn't replace it, then probably that's the reason why. So, normal in the example that was done in class, it should be 1 here, but in my situation, since I didn't replace it, it's still 2. So, yeah.
Keep talking.
That's fine. But anyways, to account for the spin, you have to go into this file, go into your in-car file, and make some modifications by adding the iSpin equals 2, and then go back and after, because you ran your VAPS the first time, now you go back after modifying this and run your VAPS again, and then you can. Then you're able to see the first spin, and you're able to see the second spin, and then if you do the grep, this command, you're able to get more information from your system, like the Fermi energy and the rest of them.
Can I make a little comment, 10 seconds?
Yeah, sure.
So there is a similarity to presentation by Kevin Gima. So in his presentation, there were 4 copies of the electronic structure, list of orbitals, right? And now in the example that Queen is doing, there are 2 copies. Physical meaning is different. In Kevin's situation, it was different key points. Now it is different spin projections, but format of files is similar.
And then you go, oops, sorry. Then you do the command grep now outcar, and like I said, it shows you the total number of electrons in there. And here it shows you if you break those electrons down, you have 33 homo alpha and 33 homo beta, and they sum up to 66. And then you can also obtain your pop up and pop down energy states by using more energy pop, by using the function more energy pop and more energy pop down here, and then you can be able to see this data. And then Anas talked about this preliminary states, so I'll just quickly go through that. And
Wait. But there is a difference, right?
Yes.
The codes you are running is slightly different. First line in each black boxes.
Okay, so the code is okay. What the functions, the input I provided is totally different from what Anas did.
No,
this is what.
Just read the first line of each black box.
Okay, so the first line, this one says the number of states.
No, before this, it's the second line.
Wait, here?
No, first line.
Okay.
Further.
To your right, to the right.
To the right.
Yes.
Okay. Oh, okay. Yeah. Sorry.
So here up, and what is in the second one?
The
In
second one is
block.
dust down.
Okay, good.
Yeah. So and then you provide it asks you for like information like number of states. Number of states will be provided with this like in your further in your earlier calculations, and then you can provide it here 20. And the only thing I can the number of atoms in a simulation cell to reduce to allow for enough space and reduce clustering. The last time you said we can have like a value of like 8 or something, so probably
4 plus 8.
no, not 4 plus 8. But you said we shouldn't have like very small values in there just to allow for space, no? Okay, well I think I'm confused then, but I provided 12 there from the example, and yeah. And it does the calculation for you, and it tells you if you're in the safe region or not. And then after that, we can use these functions that we all have used for to plot energy of states. But in this situation, it shows you the spin included. So you have in Anas's diagram, he had just the top part of it, but in my diagram, it shows you that it includes the spin top and bottom part of it. And you use this function to convert for to get an output, so you can go ahead and print it down here using the PDF function here. And then you get this picture. Thank you.
Okay, good.
So on slide 5, Dimitri pointed out that there are differences between your stuff and the previous one. So I think you went back.
Forward?
Yes.
This one?
More. Yeah, so here. So what is the significance if you add all the values in the rightmost column? So the first column on the left is the number of the band. The second is the energy. What is the significance of the third column?
Are you talking about this?
That's the energy.
Okay.
So go to the next one over.
Okay.
To the right?
No, the column, not number. Yeah, so you have a lot of ones. If you sum all of this column, what does that give you?
33.
Huh?
Will it give me 33? No?
Yes, it
Yeah,
gives you
so-
33.
Okay.
Which, and what is 33? The line before 33. Above.
Here?
Yes.
So it gives you the
alpha.
number alpha or
Yeah.
Yep.
electrons and beta, depending on which program.
Yeah.
Okay.
Good.
But in my situation, I think I mixed something up. So it was supposed to be, they're supposed to sum up to 65, but yeah.
More questions? Let's go to the last slide. Last slide. So, but here you are copying the data from doped, or there are 3 titanium and 1 vanadium. Therefore, you show this feature.
Okay.
So you copied from different directory, and the image shows magnetic properties, which is good. Okay, let's thank Queenie once again. And David may want to set up his presentation. So we do, and everyone who needs to present in the remaining time, please observe time. We need to squeeze our presentations a little. So now we need a little jump forward and backward, because there are several things to organize logically. So David will talk about light-to-matter interaction and UV visible spectrum in absence of magnetic phenomena, when everything are singlet and closed shell. And after him, we will be follower of the Queenie telling signatures of the magnetic properties on the spectrum. Floor is yours.
So I'm looking at absorption spectrum in the UV-vis range. And so as we start this, one of the major things that we need is in the in-car file, we have to make sure that we have the L wave equals true, because we are going to need the wave car output to perform our calculations.
Mm-hmm.
So then after that, what we need to do is we need to create some more files. We need to create the input overlap file, which is going to look something like this. So the file that we have, the first number is going to be our starting band. The second number will be our total, our final band, which in this case is 201. And then we can exit and save that. Then we're going to run this code right here, which will generate the energy pop file. And then from here we can create the oscillators, the OS string file. And that's done with this code. So then if we look at the oscillator string file, it gives us several different columns of information. We have the initial orbital, a final orbital, the oscillator strength, the transition energy, number of electrons in our initial orbital, number of electrons in the final orbital, as well as what they are right now.
Oh, which one?
These, the transition of the dipole
And
moment.
you're describing them by equation.
Yes, I have the equation right here.
So you can say just the stuff that is described by the equation.
And so in Dirac notation, we have it here, and we have mu, which is the dipole operator, listed here as well.
And your mu should be vector.
Mu
Should be vector.
Yeah.
Good.
So then when we actually start to create the plot, we use this code to create the plot, and it'll give us some output files. And then to actually make the plot, we use this program, right, or this code right here, which will give us another output file. And then finally, we use this one, which will give us a PDF file of our absorption spectra. What happened there?
It happens
Strikes again.
going between Windows and Mac.
So if you look at this, we have our absorption spectra. And if you look at it, so the one that I showed the code for is the one on the left.
It's fine, it's fine.
It's the one on the left here, and this is in EV.
Mm-hmm.
And the one here I redid it all, except I used the code that would give it to us in nanometers. Otherwise, they're the same, but. And then I also gave the code here to download it to the local computer. And then up here we have the equation to solve for the absorbance spectrum.
Conclusions?
Absorbance spectrums look pretty.
Good. Very good. Meath wants to ask something.
Where did you get all the information on the OS strength slide? Where do you find it? Like, how do you know what those lines mean?
It was in one of the PowerPoints that Dimitri gave.
All right.
That's where I found it. I assume it's listed somewhere as well, but I don't honestly know where.
Okay.
If you left alone, you just open source code of this program and see how it does output.
So how do you go from dx, ij, dy, ij, dz, ij, to dij?
So this is the sum of these three.
This is sum.
He's provoking you. You can take marker and write it on the board if you like. No magnetic field. With vector. Yes. Comma. No vector. No vector here. Comma. Comma. Yes. So vector consists of three components. It is what you wanted to answer to the right.
Oh.
Just look at his eyes and more questions? If no, let's thank David once again. And now this simple but useful presentation will be expanded by more complicated stuff with help of Ericson, who will tell how one should compute spectra for magnetic materials and dangerous reactive radicals.
Just letting you guys know, I had used the same molecule as Gage, I believe, used. It's nice, formatted already for us. I do want to start off with saying we're going to be calculating the spin up and spin down and combining these two to get the information we need to put it in one file. Makes it easier. So when we look at the spin up, these are the values we get. I believe this is what on slide 5 of David's presentation shown us. Shows the information of this particular molecule.
What is bad in this file, or what is inconvenient for us?
I don't know. What is?
According to David, what is the meaning of 5th and 6th columns?
Well, let's look.
Well, you can ask help of David, because he should remember it better.
Occupations.
You're saying a number of electrons in initial orbital, number of electrons in final orbital.
Yes. So if your your values there are 1 and 1, if your initial and final orbital both are occupied with 1 electron, is it possible to have optical transition between them?
My understanding is you only need to have. Okay, you're saying no. Okay, fine. No. Okay, no. Once again, this is just further the spin up code that we needed, or command lines. We just did sort. I'm not sure why we need GK. Can you explain why?
Explain the first part.
I don't know. I apologize for this, but I'm not 100% sure.
Then go back. We figure it out right now.
Okay.
So what happens if you look through this file further and further again and inspect it? Will it be occupations? Will be 1 and 1 all the time?
Yep.
Say no.
Okay. No, I'm saying no as in.
Okay, good.
Okay.
So which occupations you will observe?
I don't know.
It will be 1 and 0, 0 and 1, or 0 and 0.
0 and 0.
And which ones we need for healthy
Apparently
absorption?
2 and 0, apparently.
2 and 0 if it is singlet, or 1 and 0 if we are
Yep.
talking about spin. So you need to extract only those lines from this file that correspond to transitions from occupied to unoccupied.
So is this why we're combining 2 into 1?
Therefore, you are on the next slide. You're doing grep 1, 0 from oscillator strengths. So you extract only those lines that correspond to transition from occupied to unoccupied.
Okay. I apologize for.
That's fine. And the sort is just to organize and present it in a better way. But it's only for showing next line. You can skip the sort forever.
Okay.
It doesn't change anything.
I apologize for not being able to show command window. I was following his steps and I was able to show the information that he was showing. I tried multiple ways to do so. Once again, now we're going to do the same thing with the down spins as we did with the up. And we're going to combine the two, like you said, in parsing, from my understanding. Do you have any concerns at this moment? Yes? No? Okay. Now we're going to be merging the files. We're going to actually be removing the stuff we got, which is crazy, but apparently we are. And then we're actually going to be putting it into reformatting that file that we had just removed and putting the alpha beta into the OS strings. Okay.
Why?
Oh,
Why?
calculations are quicker.
Why you combine transitions with spin up and transitions with spin down into the same file?
My understanding is we need both
Yes,
to get the
correct.
information we
That's
need.
correct.
Yep. So we wanted that one file to be able to calculate the difference between the two to get the UV-vis absorption, I believe. Okay, so we're going to be putting this information in VASP output should be spectrum. Output is UV-vis. I know other people had put this in their PowerPoint as well. We're getting spectrum, and I want to actually. I know we put in these inputs. I was kind of curious on why we would care about the word count of OS strength, following the format you had.
Because computer is stupid.
Okay.
If we explicitly tell them how many lines to read, if you ask it to read more lines than is available, it will panic.
Thank you for clarifying. So it just seemed like an odd number that we're putting in. 812 has no major value with the molecule we used. And obviously these are just inputs that we're choosing to format it correctly the way we want. And then the next file, we're going to obviously be using NuPlot to create the PDF files and so on and so forth. SCP to put it on the desktop and then show it on the PDF. So this is what I was able to get, similar to what David got. So yeah, that's my understanding of this.
Okay, let's thank Meet for presentation. And on the register of, on the account of conclusions, what is the difference between spectra presented by David and spectra that presented by yourself, qualitatively?
Okay, we're showing qualitatively. I have to look at what this said.
Does David has any absorption in the range between 0 and 1 electron volt?
No, but we're also using different.
You're using different systems, but they are both open gap semiconductors.
Would that be a trap system?
No, it is due to doping that has one more electron.
Oh.
In the image by Queenie, where he has one electron in the conduction band. Say yes.
No, I don't know what the question was. My apologies. I just I'm
Okay,
trying to think as I'm looking.
let's thank Meet for enthusiastic presentation.
Thank you.
And now we have about 21 minutes left for 2 talks. So we are switching the gears drastically. We are going so far away from electronic structure, and we are starting to talk about questions that are near and dear to hearts of chemists: reactions and molecular dynamics.
Okay, sorry, everyone's running. Okay, so hi everyone. This should be a pretty quick talk, but we're going to talk about MD and thermal heating, which just kind of go together, and then what's called a nudged elastic band method. And I'll explain briefly about what that is. So everyone's given really great talks. You guys have seen, what we do here, whatever we do, when we set up our VASP jobs needs to be in one directory, so we don't overwrite files and do silly things like that. Likewise, we could set up a molecular dynamics directory, and to do that, we could use our NCAR that we've seen before. So that's special for our MD, and we'll see what that looks like. We'll need our POSCAR, our K-points, and our POTCAR. If you're not running a small local job on Photon, you're going to need your shell script for Cori or Edison if you're running in NERSC. So let's go ahead and open our NCAR. So what we see here is our adiabatic molecular dynamics NCAR. So what that means is, well, it's molecular dynamics and it's thermal heating. So we have a lot of information here. This is just one format, it looks like. Some notes that a user made here about what they were doing. But what's most interesting is this T beginning, temperature beginning, and temperature end. So it's adiabatic, so it stays with our system, so we know it has this heating that it does throughout the run. And then we have other values that are pretty standard. Here we'll see them kind of pretty consistent throughout the runs, or what we've seen out of our NCARs. So these are the two that you want to pay attention to in this particular NCAR. Now you could also it could also look like this. So say you didn't have a whole bunch of lines in between. So this is pretty easy. If you paid attention to the last slide, where is the information located? Who wants to answer the question? Where do you find the thermal heating? No, like it just where in this file?
Something that starts with a T.
Yeah.
T, B, E, G.
Yeah, exactly. So, and the end is this one. Well, I didn't make a note of myself here, but is this adiabatic? Yes, this is adiabatic. So the last one said it was adiabatic, but if I didn't know, you kind of clue yourself in that this is the little thing I did. It's just note keeping for yourself. So in VASP, for all the input files that we talked about, right, in Lab 7 or the Ignis talk, in Cori we use the debug shell script, and then a Photon we use that, the tilde-bin to run it. Okay, so after the job is finished, the goal of Hugh is to assign momentums to each ion. So the question is, where is this information stored? Well, it's stored in the Kant car. So as we had talked thoroughly, you guys had talked thoroughly about what all this means, and then we have the position, transit position of the ions throughout the run. So I didn't mention this before, just to take a step back, but for folks that are wondering what the really simple, I'm sorry, I have a cold, definition of molecular dynamics is it really allows one to predict the time evolution of a system of interacting particles. Just a really easy way to remember that. So just know that that's kind of what we're doing here in this case. And this will probably look familiar for me. We did this in lab, so just to know where that came from.
Can I interrupt?
Yeah.
So are you going to answer where this information is stored?
This information is stored in your that file that I just pointed out. Or are you saying that
Which part of this file?
The whole thing?
No. Anyone wants to help? Or information about momenta of each ion is stored. Like here we count 8 plus 4, 12 records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So up to here, those are positions, X, Y, and Z. And where are the momenta?
It would be probably below.
Exactly. So
Yeah,
below there is another segment for momenta. Make sense?
Okay, so that's position, and then as Dimitri said, below that is the momentum. Okay, so to see how the temperature depends on time. So after we run everything in VASP, we get all those beautiful files at the end. We get our out card and everything, and so we get this Aussie card. So we could grab our T from there, and that gives us the temperature at these particular time steps. So, and that shows it right here. It's a really big file, so I only showed you the top 5 lines and the top last lines. So, and grep T gives you the whole thing. So, but the question is, well, can we plot this? Yeah, sure we can. Let's go to. Okay, there we go. And you open GNU plot in your directory, and.
Can you go one?
Yeah, sure.
Okay, so it seems missing. Here you're showing, just put it on the screen, and in the next slide it looks like you are using it if it was placed into the file. So you need to tunnel this information into file, right?
Oh, did I miss something?
You just forgot to catch it.
Oh, okay. Okay, so we'll just pretend that you know where you are, and so you.
The information from previous slide is stored into file named T capital T capital.
Yes, yes.
Good.
So you open up GNU plot, set your dummy terminal, and then go ahead and plot your TT. You're indicating, the line widths or with lines, and you get this. And we saw this before last time in class. This is just a really quick way to just show that This is a little weird because what it's supposed to be doing is kind of like this and then slowing down, but this one maybe had some problems because this was from our case where we might have had some atoms pop off in our system. So, but you might get something like this, or you might get something that's completely different. But it gives you a really quick view. It's supposed to kind of oscillate. Like it oscillates.
If you do it long enough, it will converge to requested temperature.
Right. So long time is a good time, but be careful. Don't run on photon, run it on the NERSC because it will give you, you can use a lot nicer cues to run it on. Okay. So to create a movie of the job you just finished here, you could do this in Corey or Edison. Shouldn't matter. So we have this. Just know where you're at, what you're doing, and this. I guess this would be your position to XYZ or POSCAR to XYZ, and then you just use that. It will just generate your XYZ, but you're going to call it that. Or you
so this one will just convert your point car into XYZ, single slice.
Yep, and then this one is your X data. I'm trying to understand that to XYZ. What is this? What's this supposed to represent? Is this the same thing as this, or is it different? So,
there is a file named x.car that duplicates information from outcar.
Okay, so find that, and then you could. It should work. Either one should work. I do not Gausview, if you had something small, would be okay. VMD for everything else, because much larger systems are easier to view in the VMD, and it can do a lot more.
So which file appears after you run this x.to XYZ?
It's going to be at XYZ.
What XYZ? No. Anyone wants to help? Just repeat louder. Movie. So
It's just movie, yeah.
Movie.xyz.
Yeah.
Okay.
But can't you also name it this, or does it matter? Can't you? No, it wouldn't go from constant
The
to
first
constant.
line just converts the last step of your running into XYZ without any moving, without just last slice. And the second line creates a sequence of snapshots.
Oh, okay. So this should really not be in order. This should be a step 1 and step 2. Okay, that makes sense. Apologies, folks. And then now we'll talk quickly about the NEB. So the nudged elastic band theory just simply is a method to find saddle or minimum energy paths between the reactants and the products in this case. And VASP supports this method. You could make subdirectories, and it must be created in the directory. You have one POSCAR file, and then the images or the tag images or the number of images used specified in car forces VASP to run the elastic band method. So this is just an example where you see I decided to add images 6 that defines the number of intermediate geometries along the reaction path, and then spring is -5 is an arbitrary value that shows here, tangential springs to keep the image equidistant. And everything else pretty much stays the same. I didn't run this, but I encourage you guys to run this to see what it looked like. I came up with a file, I'll show you what I got here in a second. Post-processing, after the VASP has finished, collect the total energies and the images from the outcar files. That should be 0, 1, 0, 2, 0, 3 subdirectories because you're going to have several of them. And then you could plot the calculated and interpolated energies using show barrier function, GNU plot, or X and Grace. It's just another way of doing it, just a different way to plot. And the energy is obtained from the interpolated data. So it look like this, but it could also look like, that just shows you what you would see at a typical, okay, hold on. If you had like a local maximum, but you could also have something like some type of local minimum. Could also occur, or like we commonly see, you could probably have something like where it's kind of like this, or something like that. So you have like this kind of saddle point that's came here. But this was just a really, really easy system that just I'm not going to tell you what it was. I'm just going to say it's a small molecule of something like 4 atoms or less than that. So it was very easy to get that. But if you have something more complicated, you might have multiple points and multiple minima and that kind of thing. So that's it.
Okay, thanks. Any questions? And next,
So can you go back to your last slide?
Oh, sorry?
Because from what I know, the last slide's a saddle point. What you drew could be a saddle point, but it's difficult to know because you're showing along the perpendicular
And set up your presentation.
axis
Oh,
of the lowest.
You continue discussion without image.
Right, because the saddle point is 2 parabola's intersect.
Okay. So you're thinking.
That's going along the one that's like this, where you drew this saddle point going up. So
Well, it's my drawing might not be a very good picture.
Okay.
I was going to quote the YouTube video.
No.
No.
Okay, so
So-
what was your question?
I guess I was just clarifying, that could be a saddle point, but what the NE whatever would look like that for a saddle point.
Maybe. Any thoughts, comments?
I'm just saying, when you drew it like that, that's probably not the best representation.
Guys,
Okay.
to describe saddle points, you need more than 1 dimension.
Okay, so this
Your
is.
discussion is not possible without second dimension.
Okay, so I need more than
More
dimension.
questions?
Okay.
If no, let's thank Mer once again. And last but not least, presentation for the last 7 minutes with critically important practical skill on converting movie.xyz files introduced by previous speaker into
into an MPEG movie. Yeah.
Yep.
So I'm Kurt Altenburg. I'll be going over installing and using VMD to create an MPEG movie you can then upload to YouTube. To download the software, you will need to create an account with the University of Illinois to actually download VMD. And then you also need a piece of software called VideoMock. You don't need to pay for the license, you just need to have the software available on your computer. And the links there were at least good last night, so I imagine they're good today as well. Loading data into VMD. Has everyone in here used VMD before? Looks like most of the class, so good. Get the files off the server, start VMD, go to File and select New Molecule. Then in the new window, browse to where the files have been downloaded onto your local machine. There should be an XYZ file called movie.xyz. Load that select that file and then load it into VMD. This is just a screen capture of the final step of that process before you actually click load. Changing the molecular model. Once you get it actually loaded in, it'll be just some little lines. If you want to have something that looks a little more traditional, go to drawing method and select CPK, and you'll get the more traditional molecular model that you see here. Creating a video. In the VMD main, so when you load VMD, you get the 4 or 5 windows that appear. Go to VMD main, go to extensions, the visualization, and select extensions, visualization, and then select Movie Maker. Then you'll need to specify the path to VideoMock. So and you'll get this nice little error message. I do every time. Hopefully, not everyone's machine is like that. On my machine, and I would imagine on most Windows machines, as long as you use the default settings, should be under C, Program Files, VideoMock, and then the last part would be VideoMock.exe. Click Make Movie, and VideoMock will start. I don't have a good picture of that, but it'll start VideoMock. It'll load in all the individual frames, and it'll give you just some nice little click-through menus where you can say Create Movie, create the movie. It'll put all the frames into a nice order, and then we'll save it to a file folder. Make sure you actually click on Browse and select the file folder you want it saved to. Otherwise, at least on my software, it defaults to the file location of VideoMock, and so you'd have to scroll back and try to find that. Create the movie again and navigate to
actually runs. Yay. And there we see a titanium nanowire wiggling at 500 Kelvin. And from here, then you could take this file, its output. I was able to get the output as an MPEG video, so you can then also load this to YouTube or stick it into your PowerPoint presentations. And I was going to go over VMD is actually a very powerful tool. So some other interesting bits I found was you can once you load your molecules into VMD, you can output them as a different 3D file rendering. So I was able to output them as an STL file, which then you could actually take over to a 3D printer if you wanted to have a nice 3D printed model, or want to have it embedded in like a web page, so someone can actually go to your website and then they can move the molecule around and see what it actually looks like. Oh, and VMD does also have a command line. If you type help, it'll give you a bunch of interesting links to useful software and information, such as Babel and the actual documentation on how to use VMD. And VMD can also do scripting, although I didn't get too much into that.
It was conclusions.
Yes.
Okay. Let's thank Kurt. And any questions in the remaining couple of minutes? It is the main resource of the main tool for the next things that we will be doing in class. So how to install and run molecular dynamics in VMD. If there are no questions, it means everyone understood and can install VMD on the personal software, right? Okay, then let's thank Kurt once again. Yep. So many thanks to all presenters. All talks went successful. Everyone gets credit equivalent to 2 successful homeworks. And next evening, we will meet on the regular 5 p.m. lab and start your research projects. So building models and submitting them for initial optimization and planning next steps.
Also, it'll be like an independent kind of study thing?
Yes. Okay, let's thank all speakers and depart and see you tomorrow.